Hey pre-calc students, this is going to be your next lesson in Unit 4B, and this actually is going to be a partial combination of taking some notes on page 8 in your packet. So if you open up the packet to page 8, you can start taking some notes there, and then eventually once we're done through page 8, we might actually need some paper to do some additional practice on. So today we're going to really start focusing on how do we find algebraically roots of higher order polynomials. We've seen on the calculator how we can do it, but if we have a cubic polynomial and eventually maybe even a fourth degree, how do we start an algebraic process that allows us to find our roots? So you can see we have a chart up at the top where we have an expanded form. We're going to start with just actually a numerical value and then some polynomials. We're going to look at what it looks like in a factored form, a quotient form, and then we're going to talk about the roots. So, 15 in factored form might look like this: 5 times 3 as a quotient. 15 divided by one of the factors would give you this result. We're more used to seeing this in a polynomial format, right? So if we have x squared plus 6x plus 8, this actually is nicely factorable into x plus 4 times x plus 2. So then what would that look like in quotient form? We would take the original polynomial, x squared plus 6x plus 8, and divide by one of those two factors. Doesn't matter which one we write for now. If I were to put x plus 4 down here, then x plus 2 is the result from that division. So that might be what quotient form looks like. And then we want to connect all of this to, all right, well then how do I actually get the roots? How do I get the solutions? Well, if this factored form was set to 0, we would have roots at -4 and -2. So with quadratics, we should have a really good sense as to how to do that at this point. We have multiple techniques for solving, but today what we're going to focus on is mostly if we can write something in a quotient form, we can easily identify these roots. Now, the tough thing about a cubic polynomial is that we don't always have a technique to factor it. In fact, this one's not factorable. Sometimes factoring by grouping might work if you think back to Unit 1 in this class, but grouping is not a technique I can apply to this one right here. So to get started, I'm going to have to tell you what one of the roots are. And if you noticed over here, I'm telling you that x equals 2 is a root. Well, connect that to what that means is a factor. Okay, so what does that mean as a factor? Well, if -4 and -2 are roots, oh, look how that connected to x plus 4 and x plus 2. So this would mean that x minus 2 is one of the factors, which means that when I divide x cubed plus x squared minus 10x plus 8 by x minus 2, I'll get a result of a polynomial that in this case winds up being quadratic, right? If I divide a linear into a cubic, we're going to get a quadratic factor that's left. And whatever that quadratic factor is, I can then solve that and get the remaining solutions. So how are we going to actually find what that quadratic result is? Well, we're going to do the long division process. So polynomial division is something that you would have learned how to do in Algebra 2 last year. So let me recap what that process looks like for you. We're going to take x minus 2, and we're going to divide that into the cubic x cubed plus x squared minus 10x plus 8. Okay. The process for polynomial division is the following. You take the first term underneath your division bar here, x cubed, divide by this x on the outside. So x cubed divided by x is x squared. The next step in the long division process is we now multiply the x squared times your x minus 2. So we did our first division step. Now we multiply through to get x cubed, and then that's going to become minus 2x squared. If you remember anything about long division, the next piece of the process is to subtract. Okay, subtracting is where things get a little tough sometimes for students because x cubed minus x cubed, that's the easy part. But they forget to carry that negative over to the 2x squared. So if I distribute that negative across, now this becomes a positive 2x squared. And x squared plus 2x squared is 3x squared. So just be careful about that one step there, distributing the negative all the way across. But bring down the negative 10x and then start the process over again. Take this term 3x squared and divide by the x on the outside. 3x squared divided by x is a positive 3x. Take your 3x, multiply by x minus 2 to get 3x squared and then minus 6x. Going pretty quickly through this process. So of course, if you need to slow it down, you guys know how to do that. All right. So now that I've multiplied through, we have to subtract. Well, yeah, 3x squared minus 3x squared goes away. But if you distribute that negative over here, now it's a plus 6x. So negative 10 plus 6 is negative 4x. And we're almost there, but we got to bring down the plus 8, kind of our last step here. Negative 4x divided by x is a negative 4. Distribute that back into x minus 2 to get negative 4x plus 8. And lo and behold, when you subtract those, you wind up getting 0 as a result, which is pretty awesome because what that means is we know that that's the remainder. It means that x minus 2 divided in evenly to this polynomial. So the results, the quotient of x cubed plus x squared minus 10x plus 8 divided by x minus 2 is in the end the quadratic x squared plus 3x minus 4. So we can actually come back over here and write that as, this is actually what we would have in a factored form. These two would multiply to give you this cubic polynomial right here. So now that I have that written out, could we find the two remaining roots? And the answer is, of course, we can factor this, right? The quadratic that you're left with isn't always factorable, but in this case it is. It winds up breaking down to x plus 4 times x minus 1. And when you have that in a factored form, now I can see that the other two roots would be at x equals negative 4 and x equals positive 1. So this will be some of our initial stages getting us ready to find all the roots of a cubic polynomial. To start, I might have to give you a little bit of a hint. Eventually, we're going to take all the hints away. But my hint was, hey, x equals 2 is a root. So what that means is that x minus 2 is a factor. And then if I do the polynomial division, I can get the quadratic that's left. And that quadratic gives me the other two solutions. A lot of pieces that we're putting together there. And this polynomial division process, again, I did go through it pretty quickly, in my opinion even, but it's definitely a little cumbersome. It's a little bulky. Maybe if I had a 4th degree, it's going to take even more steps to divide, a factor in. So you'll be very pleased to know that there's an easier way. And the easier way that we're talking about is a process called synthetic division. Synthetic division is a process that only requires us to use the coefficients of the polynomial here. And it requires us to test the root that is a result of this factor x minus 2. So let me show you what synthetic division would look like. I want you to make kind of this little half box over here and put x equals 2 in it. Remember that 2 was the initial root that we were given. The other thing I just said about synthetic division is it only requires us to use the coefficients of the cubic polynomial we're dividing into. Those coefficients are 1, 1, negative 10, and 8. Okay, so literally just copying those coefficients down. And we're going to see how using synthetic division, I'm going to get the same result that I got, and you're going to like it a lot better. Ready for this? First step, bring down the 1. You're always going to multiply by the root that we're kind of testing out here. So we're going to multiply by what's in this little box here. 1 times 2 is 2, so write that on the next step. And then add it to the coefficient above. 2 plus 1 is 3. And then repeat that process over again. Multiply by what's in the box. 3 times 2 is 6. Add it to the negative 10 above to get negative 4. Last step, negative 4 times 2 is negative 8. Add it to the 8 above and you get 0. Synthetic division is now complete. So you may not quite understand yet how it connects to all this mess from over here. But start looking at what the result was, right? Here was the results. We had this polynomial with a remainder of 0. Do these numbers look familiar at all? 1, 3, negative 4, 0. I bet you're starting to figure it out. I'm going to actually separate that last 0. What does the last number always represent in a division process? It is the remainder. Okay, so when you get 0 as a remainder, that's typically good news for us. It means that 2 is a root of this polynomial. Where did the 1, 3, and negative 4 go? Well, the 1, 3, and negative 4 are the coefficients of x squared, the x term, and the constant in your polynomial. So we now have x squared plus 3x minus 4 is the quotient. That's what's left. And of course, if I factored that, I would get these two remaining roots at negative 4 and 1. So that's the great part about this, is that I'm getting the same exact results. I even get the quotient, that quadratic, that if I needed to factor and keep going with the process here, we can very easily do that. So if I gave you these two options, polynomial division versus synthetic, I bet there wouldn't be a single student to choose polynomial division. And guess what? You can always use synthetic division. Okay, so that's the good news. Are there benefits to polynomial division? Yes, there are. But for our purposes and what we're going to do in this unit, I don't think we'll have to rely on it really ever. So let's use a synthetic division technique to do x cubed plus 2x squared minus x plus 5 divided by x plus 1. Okay. So to connect this back to the example that we just did, when we divide by x plus 1, if x plus 1 is a factor, that means that negative 1 is the root that we're testing. That's the root that goes in this little box right here. So be careful that we don't write positive 1. It's going to take, just a little time to get used to. Then I get to copy the coefficients down from the cubic, which are 1, 2, negative 1, and 5. And if you remember that process from a moment ago, the very first thing I did was I brought down a 1. So when I bring down the 1, 1 times negative 1 is negative 1, plus the 2 above it is 1 again. Well, 1 times negative 1 is still negative 1, plus the negative 1 above it is negative 2. Okay, one more time, negative 2 times negative 1 is positive 2, and then 2 plus 5 is 7. Remember that last number, just like I did in the last example, I kind of block it off because that's the remainder. So there's a couple things that we can do in the end. We can write this as a quotient plus the remainder. So the quotient is x squared plus x minus 2, right? That's 1 is the coefficient of x squared. This one's the coefficient of x minus 2. But since we were not up to the remainder of 0, that remainder of 7 would have to get divided by x plus 1, what we were dividing into the cubic to start. So this expression right here is equivalent to what we have written up here in number 1. If you do the division, we get x squared plus x minus 2, but plus the remainder of 7 over x plus 1. So what's the conclusion that we can come up with based on all of this algebra? We know that x plus 1 is not a factor of the polynomial that's given at the top. It didn't divide in evenly. We didn't get that remainder of 0. And if x plus 1 is not a factor, that means that negative 1 is not a root of the polynomial. And our whole goal in this unit is to find roots. So it's okay for now. We're not going to actually just keep searching for roots in this one quite yet, but our whole process moving forward eventually will be, all right, if negative 1 doesn't work, well, what should I try next? But for now, let's just stop and make sure we have a good idea about what's going on with synthetic division before we start really digging deep for finding all the roots. Okay, number 2. Let's try x cubed plus x minus 3 divided by x minus 2. And I think as you're writing that down, you're like, oh, wait, silly Mr. L, he forgot to write something on the top. He forgot that there's usually an x squared term when you're writing a cubic polynomial. Well, there usually is, but there's not always. So be really careful. There's no x squared term here. So when I go to do the synthetic division and I write the coefficients down, it's imperative. Big word there. You need to have 0 as a placeholder for the x squared term. Otherwise, I promise you, you will not get the correct answer. Okay, so we're going to go ahead and do that in a second, but this is an important step. It's very easy to forget. Okay, so when I divide by x minus 2, what's the factor that we're testing in the box? It's positive 2. So continue to be careful about that. All right, what are the coefficients? Coefficient of x cubed is 1. Coefficient of x squared, 0. Don't forget to include that. Coefficient of x is 1, and then -3. Okay, so bring down the 1. Synthetic division would say multiply by that 2, so that's 2. Add to the 0 above, that's 2. 2 times 2 is 4, plus the 1 above it is a 5. 5 times 2 is 10. 10 plus -3 is 7. Okay, that's my remainder again. So the conclusion here is that in the end, 2 is not a factor of this polynomial. Okay, but if I asked you to write the quotient and the remainder, the quotient is x squared plus 2x plus 5 plus 7 over x minus 2. Okay, there's your quotient. We might get into some specific questions where I ask you, is x minus 2 a factor of x cubed minus 5x plus 2? So in the end here, even though the conclusion is, oh yeah, x equals 2 wasn't a root of this polynomial, here's a specific question that's asking kind of right out, is this a factor, meaning is x equals 2 a root? And the polynomials changed a little bit from the last example, but I hope you're noticing we're missing that x squared term again. So if I try x equals 2 as a root, the coefficients are going to be 1 for x cubed, 0 for x squared, -5 and 2. Bring down the 1. 1 times 2 is 2, plus the 0 is 2. 2 times 2 is 4, plus -5 is -1. Last step, -1 times 2 is -2, plus the 2 above it is 0. Got it. So when you get that 0 in the end, if the remainder is 0, conclusion, x minus 2 is a factor of this polynomial, which implies that x equals 2 would be the x-intercept. X equals 2 would be the root. Okay. Do you have to put a smiley face when you have that 0 as the remainder? The answer to that is yes. It is a necessary step. Otherwise, I'll take off points. Okay, last one. Is 2/3 a root of 54x cubed? Uh-oh, get ready for it. Minus 27x squared minus 27x plus 14. Yikes. Pretty big coefficients. A fractional root. Can we do it? Of course we can. We've got this. Okay. Now I want you to look at how these last two questions were asked. Is this a factor? Is this a root? They have a similar concept, but the way they're being asked are slightly different. So when I ask you if x minus 2 is a factor, notice how we had to say, oh, x equals 2 would be the root that we're testing. If I give you the root, 2/3, that's the number that goes in the box. Don't change the sign here. It's different than being given the factor. Okay, so make sure you put 2/3 in the box. The coefficients of the cubic that we're given are 54, -27, -27, 14. All right, so we got to bring down 54. I have to multiply it by 2/3. Oh man, all right. Well, 3 goes into 54 18 times. Maybe you're not as familiar with that, but you guys can figure it out. 3 goes into 54 18 times. 18 times 2 is 36. So add that to -27 to give you a 9. Multiply by 2/3. This should be easier. 3 goes into 9 3 times. 3 times 2 is 6. 6 plus -27 is -21. 3 goes into 21. You get -7. -7 times 2. Uh-oh, look at that. -14. Added to 14, of course, would be 0. So to answer the question, is 2/3 a root? Sure is. Okay, and we usually get excited when we find roots because then in the end, we can now have a quadratic, right? I mean, this would have been x squared plus 2x minus 1. I can try and solve that and get the remaining 2 solutions there. Same thing here. This one would be a little bit tougher, 54x squared plus 9x minus 21, but we have a lot of good strategies and techniques that help us to solve quadratics. So that's it for today, just a little bit of practice in this idea of synthetic division. there is much, much more synthetic division to come in this unit, so get ready for it. One of my favorites, all right? Have a great rest of your day.